Hey everyone, we're getting into our longer questions, free response questions that we're doing for our Chapter 6 test. And we're going to start off with this first one, which is a little bit crazy as far as the numbers go, but nothing too bad. Let's see what happens here. One afternoon, Arina charted the temperature in Woodland Hills. At 3:30 it was 73 degrees, at 4 o'clock it was 75, etc., etc. By the time it got to 8:30 it was 66 degrees, so it was actually a really nice day in Woodland Hills. It rarely gets that cold. Well, maybe not rarely, but definitely not in the summertime. And the thing that I said was going to be crazy comes right here. We're going to say t equals 0 is 3:30. So I'm going to go ahead and erase that and put a 0 up here. And that would make 4 o'clock 0.5, half an hour later. 5 would be 1.5, an hour after that. An hour after 5 o'clock is 6 o'clock, so this is now 2.5. 3.5, 4.5, and then at 8:30, half an hour after 4.5, that's just going to be equal to 5. Question A, use a left rectangular methods with 6 rectangles to estimate f of t integral from 0 to 5. And then use a midpoint rectangular. Now midpoint is in quotes, so we're not going to use actual midpoints. We're just going to look for some point in between. Think back to when we were doing the Riemann sums. It didn't matter where we evaluated the function, as long as we evaluated the function somewhere in the interval. So that's going to be kind of what we're going to use for the midpoint, quote unquote. Well, let's do the left rectangular method first, and I always like to say make yourself a chart. So let's make our chart. Our first one is the intervals, and our first interval is 0 to 0.5. Then of course 0.5 to 1.5, 1.5 to 2.5, 2.5 to 3.5, all the way to this very last one. Next line we're going to do is our delta x. So we've got delta x, and I'm going to write the word delta here. Not a big deal. 0.5, 1. 2.5 minus 1.5 is 1. 3.5 minus 2.5 is 1. 4.5 minus 3.5, that's 1. And this last one is 0.5 as well. Now we're using a left rectangle, so we're doing the function f evaluated at x on the left. So what's on the left side of each of these intervals? The left side of this first interval is 0. So f of 0 is 73. So let's put a 73 here. The next interval, our next interval is f of 0.5, and f of 0.5 is 75. Again, we're just looking in the chart over here. There's where that 75 came from. F of 1.5, again, looking at the chart, that's just 75. So we'll put another 75 here. F of 2.5, that is 72. So we'll put ourselves a 72 in our chart. And the next one is f of 3.5. F of 3.5 is 70. So we'll hang a 70 up in our chart over here. And then f of 4.5 is 66. Notice that we are not going to use 66, this 66 over here. Every time we use a rectangular method, we actually don't use one of either the left or the right. Okay. Finally, we're ready for the integral. So the integral is going to be approximately, let's see, 0.5 times 73. That second interval is 1 times 75. Okay. Make sure you're writing. Don't be too smart. We're going to multiply 1 times 75 here. The reason we're doing this is we want our audience, whoever is reading our paper, we want them to see what we're doing. We don't want to hide our mathematics. Next one is 1 times 70. So when you skip a step here, you're just hiding a step which might be worth points. You never know. Actually, in this one, I do kind of know. You would get points for writing all of this out. Okay. Next, you're just going to calculate all of that. 361.5. So that's our left rectangular method. The next one would be a midpoint rectangular method. And for this one, we're going to need another chart. So in this method, we're going to have to make our interval width 2 of the squares that we see over here. So we would go from 0 to 1.5. That's going to be our first interval. 0 to 1.5. Notice how that kind of has 0.5 positioned, I guess, in the middle. Our next interval here, we're going to go from 1.5 to 3.5. Again, that's spanning 3 different measurements. So 1.5 to 3.5. Next, we're going to go from 3.5 to 3.5 to 5. Okay, that's going to be our last interval. Again, spanning 3 different measurements. Okay. Now, we're going to next in our chart put in our delta x's. So delta x. 0 to 1.5, that's a delta x of 1.5. 1.5 to 3.5, that's a delta x of 2. 3.5 to 5, that's a delta x of 1.5 again. And next one is f, evaluated at the middle. So this first middle, let me clear off this so it's a little less messy. Let's clear this off, and our first middle would be, I don't know why it's not erasing. So from 0 to 0.5, here's our first middle, 75. Okay, what's between 0 and 1.5? It's 0.5. So our middle is f of 0.5. Maybe I should write that. And that's equal to 75. Okay, our next middle is going to be f of, okay, our interval goes from 1.5 to 3.5. What's in the middle there? Well, it's 2.5. This time it actually is in the middle. So f of 2.5, I'm looking in my chart right over here. That's equal to 72. So let's put a 72 in our table. And then our last interval, what's in the middle of 3.5 and 5? Well, the only one that's close to the middle here is 66. So that's what we're going to put in our chart here. F of 4.5 equals 66. And just like before, we're going to write out our integral, and then we're going to write out our sum of products. Sum of products, yeah, that's right. 0 to 5 of f of t dt. That's going to be approximately equal to 1.5 times 75 plus 2 times 72 plus 1.5 times 66. And when you multiply that all together, you get yourself a 355.5. Now that's already a lot of work for part A, but rest assured, if this was actually a problem on like an AP test, you would only have to do one of these rectangular methods. The fact that we're including two is just to give you more practice for your test, so you'll know a little bit more about what to expect. Next one, use a trapezoidal method to estimate. So again, I recommend you put together a chart. So let's get a chart. So this chart starts an awful lot like the previous one that we did for the rectangular method, but now the big difference here is instead of calculating the height on the left and the height on the right, we're going to find an average of the two heights. I didn't want to keep scrolling back and forth and giving you whiplash, so I just went ahead and I've copied that chart over here. So the first one, what is the average of 73 and 75? Well, that is 74. Next one, what is the average of 75 and 75? Well, that's 75. Next one, what's the average of 75 and 72? Well, that's 73.5. Next one, what's the average of 72 and 70? That's 71. Almost finished. What's the average of 70 and 66? That is 68. And finally, what's the average of 66 and 66? Well, that's 66. And again, just like before, we're going to go ahead and write our sum of products. So the integral from 0 to 5 of f of t dt can be approximated by 0.5 multiplied by 74 plus 1 times 75 plus 1 times 73.5 plus 1 times 71 plus 1 times 68 plus 0.5 multiplied by 66. And when you multiply that all together, so take a look, we got 357.5. So take a look, that's what I meant to say. Take a look at the three results that we got for estimating. 361.5, 355, 357. Now all of those are pretty similar. So that makes me believe that we're actually kind of doing this correctly. All three of these should be similar because we're estimating the same thing in each one of those. Okay. Now, use our answer in part B to find the average temperature in that 5-hour interval. So this is the average formula, average temperature. That's going to be equal to, now the average of anything in calculus is 1 over b minus a integral from a to b of whatever the function is. So in our case, a and b are 0 and 5. So 1 over 5 minus 0 integral from 0 to 5 of ft dt. Well, we have an estimate for that integral. Our estimate for that integral was 357.5. That's what we got in part B. And when we do that division, 71.5. So take a look at that temperature. Take a look at the temperatures we see here in our table. Does it seem plausible that the average temperature is about 71 degrees? And looking at what I see here, yes, it is plausible. 71 degrees fits nicely along with all of the data. It's not too hot of a temperature in terms of the rest of the data. It's not too low of a temperature in terms of the rest of the data. It's kind of right in the middle. So 71.5 sounds plausible for our average temperature, which means we're going to be okay here. Okay, letter D. Find the integral of f prime of t dt. Now this is, I don't want to say it's a trick question, but it makes sure what you know what you're reading here. The integral from 0 to 5 of f prime of t dt. What's the antiderivative of f prime? Oh yeah, the antiderivative of f prime is just f. So this is equal to the antiderivative f evaluated at 5 minus the antiderivative f evaluated at 0. Going back to that chart, f of 5, that was 66. Somehow I remembered that number. No, f of 0 was 66. So maybe I didn't remember anything. F of 5 in my chart was 66. F of 0 was 73. So this is 66 minus 73. That's equal to negative 7 degrees. I know it's degrees because F is in degrees. So what does that represent? Well, if you just take a look at the function, don't worry about anything else. If you subtract f at 8 o'clock minus f at 3 o'clock, that's just a change in temperature. So this means that the temperature in Woodland Hills dropped 7 degrees from 3 p.m. to 8 p.m. That's all it means. When you subtract two temperatures, that's going to tell you the temperature change. So it's a change in temperature from 3 o'clock to 8 o'clock. All right, that's it, everyone. That's a kind of a fun problem, to tell you the truth. Maybe it's kind of tedious because you're doing a trapezoidal sum and a rectangular sum and a midpoint sum, but you know, that's really good practice for you so you can tell the difference between them. Word of advice to you, a lot of students mix up the midpoint rectangle with the trapezoid it's not even a rectangle, with the trapezoidal sum. They get those two formulas mixed up even though they're, you know, basically really different from each other. So be on the lookout for that. Try to remember the difference between the midpoint formula and the trapezoid formula, and everything hopefully will work out great. We'll see you next time for more calculus.